Good morning, everyone. I, Peeyush Sharma, Assistant Professor, IIMT College of Science and Technology. It's my pleasure to welcome you all in today's online lecture on RedBlackTree. So let's start. RedBlackTree. So before uh, come to the topic, let's see some terminology related to the tree. So what is the tree? So basically, tree is a non-linear data structure. There are several types of data structure uh, in which one of them is non-linear. So tree is a non-linear data structure where the data is represented in the form of hierarchical. That is, we can say in the form of parent and child. Uh, some terminology related to tree. Let us discuss about it. Like uh, when we talk about tree, there will be a root and child node, parent node, sibling, leaf node, internal node. So what is root? Root is basically the first node, or we can say the parent node of all child node. And internal nodes are also represented in the form of parent and child. So we can see here, uh, like first node is the root node, second node is the parent node, and 4, 5, 6 nodes are the child node of the second node. And the next terminology is sibling. What is sibling? Here we can see that first is the root node and second and third is the child node. So third will be the sibling of this second node and second node is also the sibling of this third node. Similarly, 4, 5 and 6. We can see that 2 is the parent node and 4, 5, 6 is the child node. So 5, 6 are the siblings of this fourth node and similarly 4 and 5 are sibling of this sixth node. And also we can see that 8 is the sibling of the seventh node and as well as 7 is the sibling of this eighth node. So these are some terminology related to the tree. So what next? Trees are basically, there are several types of trees in which we can say one of them is the binary tree. What is binary tree? Binary tree is a collection of nodes that consist of root and other subsets of the root points, which are called the left and right subtree. We can see here, one is the root node and 2 and third are the child nodes. So 2 and third are the child nodes. There are two child of this root node, that is 2 and 3. But after that, when we talk about 2, there are three child nodes of second. So this is not a binary tree. This is a ternary tree. So what is the binary tree? A binary tree in which we have only two child nodes. Basically, we can say either not any child node or only one child node or at most two child nodes. So that will be a binary tree. Here we can see that this is not a binary tree. Why? Because C have three uh, child nodes. So these are some terminology related to tree. Now next topic is types of tree. So there are so many types of tree in which we are studying here in the form of balanced. So there are two types of tree, unbalanced tree and balanced tree. These are basically in the form of balanced. So there are two types of trees, unbalanced tree and balanced tree. Unbalanced tree You can classify balanced tree as a binary search. We have seen, or in data structure there is a concept of binary search tree. What is binary search tree? In binary search tree, the left node is less than root node, or we can say parent node, and right node or right subtrees node, child node is greater than their parent node. So that is binary search tree. And when we talk about the balance tree, there are categorized balance tree in the there are several uh, types of balance tree. That is ABL tree, red black tree, B tree, also a balance tree. B plus tree is also balance tree. So why these so many are balance tree? If we have already ABL tree, so why red black tree? Why B tree? Why B plus tree? So let us understand why so many trees. We have avial tree. Basically, avial tree is a balanced tree. And when we say balanced, then what is the factor which is defining that this avial tree is balanced in the form of balance? So avial tree have categorized uh, balancing factor, right? So ABL tree is in the form of balanced tree on the based on the parameter that we can say is uh, uh, balancing factor. What is balancing factor, or what is the factor that defines that the ABL tree is balanced tree? That is basically uh, when we say the right child of the parent node, the height of the right child of the parent node, and the height of the left child of this parent node, or uh, not child, subtree. The difference between left subtree of a particular parent and the right subtree of a particular parent. So the difference between the height of the left subtree and the difference between the height of the right subtree will determine whether our tree is balanced or not. And the difference would be in the form of +1, 0, and -1. That if our tree is in this balance form, this balancing in factor, that is +1, -1, and 0, then that tree will be we can say we called as a avial tree, right? So if we have already avial tree, then why red black tree? So what is the drawback of avial tree is when uh, we say there is a concept of skew tree, and we if we add binary search tree, skew binary search tree, what we can say that first we say what is skew tree. Skew tree is basically all the nodes are either on the right child of parent or either left child of particular parent. For example, here we can say that all the child nodes are one side, and that is only in the right child, only in the right direction, and the left child is what? Nothing. That is null. Left child is null. So in this skew binary search tree, if we see that if we talk about the ABL tree, then ABL tree have only three balancing factor, either -1, either 1, or 0. So here we see that we have only right child, and when we talk about the nth node having no either left child or right child. So what is the balancing factor of nth node? That is 0. But when we talk about the n minus nth child node, What is the balancing factor? That nth n minus nth oneth node having no left child, only have right child. So left minus one, that is minus one. So n minus oneth node having balancing factor is minus one. Similarly, n minus two. So when we talk about n minus 2, note that the balancing factor will be 0 minus 2. So there is a problem because in AVL tree only 3 balancing factor we have, either 0, minus 1 or 1, but we got minus 2. So this is not, this tree, this skew binary search tree not balanced. So we have to balance it. So for balancing it, we have to apply some rotation technique. And for this, we have some terminal, some concepts regarding rotation. So let's not talk about that factor, but if we see for skew binary search tree, we have to balance it. So for balancing it, if we are talking about AVL tree, so there we got order of n times. For balancing skew binary search tree, we have to take order of n times, right? So this is the worst case of this AVL tree, right? So to overcome this drawback, there is a concept of red-black tree. So let us see how this uh, how this disadvantage is overcome in red-black tree. So let us understand what is red-black tree, and after that we will understand that how this disadvantage is overcome in red-black tree. So let us talk about red-black tree. What is red-black tree? How to implement it? What is the difference from AVL tree and operations in red-black tree? So red black tree is a balanced binary search tree. Just like ABL tree, it is also a balanced binary search tree, right? With one extra bit of storage, that is color of the node. In ABL tree, there is a no concept of this color. But in red-black-tree, when we represent a particular node, we take an extra bit of storage, and that bit of storage is represent the color of that particular node. So is it we are really describe the color of this particular node with the help of one bit? How? So this is in the form of 0 or 1. 0 represents black, 1 represents red, right? So what is the purpose of this red-black-tree? The purpose of this red-black is to keep the tree balanced. Other balanced such tree are, so if this we have seen ABL tree and red-black-tree, and we will see later on the properties and implementation and rotations of red-black-tree. But also there are some other balanced search tree like ABL tree, 2, 3, 4 tree, split tree, and tree. So let's not discuss about this and see what is red-black-tree. We have seen here red-black-tree is a balanced binary search tree with one bit of extra storage, that is represent the color of that particular node, either red or black. So what is the properties of red-black-tree? The properties of red-black-tree is first one is every node is either red or black. First one is the node which represent in red-black-tree having a particular color, that is the red or black. And second one, the root of the tree, the root of this red-black-tree is always black, right? The root of this red-black-tree is always black. Third one is every leaf node is black. We will see here, I have written here nil. What is the meaning of this nil? But third property is every leaf node is black. Fourth property is if a node is red, then both of its sides are black. That means if a parent's color is red, then the both child of this parent color should be of black color, not red color, right? Fifth property is for each node, all simple path from the node to descendant leaf contain the same number of black node, meaning the path of each and every red black tree having same number of black node, right? So these are five important properties of red black tree. On based on these five properties, we are balancing our tree, right? So let us see some examples. So here we have here is a example of red black tree. There are several data we can see, and it is represented in the form of red black tree. The first property is what? Every node is either red or black. Yes, we can see that every node is either red or black. Second one is the root node is black. Yes, our root node is black. Third one is every leaf is is black, right? So here we can see that the leaf node having two children, there is no data on that node, and we have feel it as a nil, right? We can see that every leaf node is of black color and having data nil, right? So we can centralize it. So here we can see that all the nil are centralized in a single node. What this single node is known as the sentinel node, right? And sentinel node, sentinel node's descendant is connected to the root node. So this is all about the red black tree, right? And the property is given below. That's a red black tree. Every node is red or black. Every child node is either red or black. No consecutive red node are exist in our red black tree, right? So next, the height of this red black tree is 2 log n plus 1. And what operations we perform in red black tree? Generally generally what operation perform in the other tree, we are also perform the other tree, right? Like a tree insert, tree delete, search. And what with the complexity of these operations is order of log n, right? These are some operation: rotation, insertion, deletion, and searching. How the rotation is performed, just like ABL tree. Here is also we rotate our tree in a just like ABL tree, but here there is some concept that wise parent, if we are rotating this left side node as right rotation, so wise parent should be same as x parent, and y's place should be taken by x. So where alpha, beta, and gamma, that is the child node of x, y goes. So if we are rotating this tree, vice parents should be same as vice parents should be taken by x parents while we are rotating a right rotation. So vice parent is taken by x parent. Alpha should be the left node of x node, right? Beta should be beta. Here we can see that this is a binary search, right? So beta is greater than x but is less than y, and we are rotating right side. So this beta will be the right direction of this x but left direction of y. So here beta will become the y's left child, and gamma is as here we can see that the right child of this y. So gamma is as well. Similarly, vice versa, if we are rotating in left direction, so left direction we are rotating, x parent should be x parent taken by y parent. Gamma which is the y is right node of this y, so right node is will be here, and similarly vice versa. There is some example of this right rotation, sorry, left rotation. The tree is not balanced, so we have to rotate it, and x is here, y is here, x is 11, y is 18. 18 is taken place by this x place that is here, and x goes to the left child of this 18, and alpha beta are arranged here. Here is some code algorithm of this left rotation and right rotation and insertion. Here is the algorithm of insertion. So let us see how insertion is performed in RedBlackTree. So here is the algorithm of this insertion, but I am not going through this algorithm. Let us see some through some examples so that will be clear. So here are some data. We have to insert 4, 3, 6, 7, 11, 5, and 8 and 9. So first 4, 4 will be inserted. Initially the tree is empty. 4 will be inserted. So 4 will be the root node. Root node which always blank. Now next 3 will be less than 3 is less than 4, so it will be the left direction of this 4, and the color of this newly inserted node will be red color, right? Every node we have to insert will should be of a red color, so 3 will be of the red color. Also 6 is greater than 4, it will be on the right side, so it is of the red color. 7, when we insert 7, 7 is inserted 7, it will be of red color, so it will lie on the right side of this 6 node. But here we can see that there is a red conflict, right? So how to remove this red conflict? There is a concept of red. When we have red conflict, so we have to see the newly inserted parent sibling color. Here, parent sibling color, that is 7th parent is 6, 6th sibling color is 3. So if newly inserted node is of red color and its parent is also red color, then we see the sibling color of this newly inserted node. So 3 is of red color. Simply what we'll do, we simply recolor the parents color as well as their siblings. So here we simply what we'll do, here we recolor the parents color as well as their sibling. Now next data is 11. So 11 will be inserted on the right side of this 7, 7. There is also a conflict of this red. So how will we remove it? We can see that the sibling of this parent 11th 7th sibling is nil. Here nil having no data, but what we'll see that every leaf node is of black color. So 6th left node is nil, that is of black color, and this is not in the form of and this is not balanced. So how will balance it? We have to rotate, right? So what we'll do, we rotate. So in which direction we have rotated? Left direction. So 6 plus will be taken by 7, and 11 is as place, and 6 will goes to the left node of this 7, and after rotating what we'll do, we recolor, right? Similarly we insert 5, 5 will go to 6 left. Again, red conflict. What we can see that the newly inserted node is 5, and 5 parent is 6, 6 sibling is 11. That is of red color. So what we'll do? Simply recolor. So here we recolor our parent node. But when we recolor our parent node, what we'll see, the number of black node in each and every path is not same, right? So what we'll do, when we recolor the parent node, we also check the parent's parent node, where parent's parent node is of what color? Black color. So what we'll do, we recolor. If the parent's parent is not of not root node, so what we do, we simply also recolor it. When we recolor 6 and 11, also we check its parent is 7, which is not root node. So we simply what will do, recolor it. So here we recolor it. Now our red black tree is of balance. Similarly, we insert 8. There is no red conflict, and our tree is balanced, and number of black node in each and every path is same. Here nil is not counted in our number of black nodes. Nil node is not nil, which is actually a node. but does not, which is actually a node which is of red and black color, which will not counted in our uh, number of black node while we are counting number of black node in each and every path, right? So there is no conflict of red black, there is no violation of red black tree. Now next insertion is 9. 9 will be goes to at right hand, and there is a conflict of red black violation of red conflict, violation of red black tree. So what we'll do, simply check the sibling color. So at sibling is black. So if at sibling is black, what we'll do, simply rotate it, and while we are rotating, 11th place will be taken by 8, and 11 goes to 8 right hand side and recolor it. So we recolor. That's how we insert in our red black tree. And what is the time complexity of this insertion? The time complexity of insertion is log n. For n element, it will be n log n. Space complexity will be order of n. So there are some exercise to do. Thank you.